Hello, my name is He Yi-un, and today I'll be doing problem set 8, question 3. The question states that two strings of linear mass density are knotted together at x is equal to 0 and stretched to a tangent f. A wave in the string reaches the junction between the two strings, at which it is partly transmitted and partly reflected. For part A, assuming that k2v2 is equal to k1v1, which is equal to omega, and that the displacement of the knot arising from the incident and reflected waves is the same as that arising from the transmitted waves, show that A is equal to B plus C. I set the original wave as Y, the reflected wave as Yref, and the transmitted wave as Ytrans. Because omega is equal to k1v1, which is also equal to k2v2, as given in the problem, we can rewrite the equation with omega as shown below. String 1, the wave y1 is equal to the original wave y and the reflected wave yref. And after writing out the equation, we get this. In string 2, the wave y2 is equal to the transmitted wave, and we get the expression here. Because the two strings are continuous at x is equal to 0, so at x is equal to 0, the wave in string 1 is equal to the wave in string 2. And after simplifying the expression and canceling out sine omega t, we get A is equal to B plus C. For B, if it is assumed that both strings near the knot have the same slope, that is dy dx in string 1 is equal to dy dx in string 2, show that C is equal to this, and what conditions in C are negative. If dy dx of string 1 is not equal to dy dx of string 2, then the slope would not be continuous, and the acceleration of the knot at x is equal to 0 would approach infinity, which is not possible. So the derivative of string 1 is equal to the derivative of string 2 at x is equal to 0. So by doing the derivative and simplifying the expression, we can cancel out cosine negative omega t and cosine omega t, since it is essentially the same thing. And we get AK1 plus CK1, which is equal to BK2. And using the equation from part A, where A is equal to B plus C, we can substitute B with A minus C. And simplifying the expression, we get C is equal to this. Because omega is equal to KV, we can rewrite K with omega over V, and by multiplying v1, v2 to both the numerator and the denominator, we get v1 minus v2 over v1 plus v2 times A. Therefore, for C to be negative, v2 has to be bigger than v1.